Good morning, kids. In today's class, we are going to discuss the waves and sound one shot. In one shot, this is one very important again the chapter for JEE Mains. You'll get two questions. There's a chapter waves and sound. Two questions will get one from waves, one from sound, and for JEE Advanced also two questions. The weightage will be around 9%. A lot of concepts are there, formulas and concepts are there. Problem solving, standard numericals. What should be the strategy for first JEE Mains? Let me talk it. You watch what all I explaining now. Understand the concepts involved. Then after that, you remember all the formulas, all the ideas, what all I explained. You have to recollect the formulas. How to remember all the things? Putting effort. You have to read 2, 3, 4, 5 times. Then the formula will become memory. Then the solve the PYQ. So this chapter, the main essential things is the concepts. You should have the clarity of the concept. Concept clarity is there, then it will be very easy for you to manage this. Then remembering formulas. Then you can manage the PYQ also on your own. For JEE Advanced, again, learn the concepts, each and everything. Remember the formulas. Then solve different types of numerical. For JEE Advanced, PYQ not needed. Different types of numerical. So this is a very lengthy chapter. So around 100 problems if you can work out, no? Then for advanced, different type of numericals. It's there in my videos also I explain. So that will be enough for you for JEE Advanced preparation. There's a one strategy what you have to follow. So how to read that one? So the planning will be waves and sound one shot. So the planning. So first you try to learn the basic idea what is a wave, then the types of wave which are there in our syllabus, come across that one. Then the wave equation, what are the different parameters of the wave, that called a wave equation characteristics. Then propagation time of wave, time taken by the wave to propagate. Then the speed of the wave, the phase of a wave, then energy, power and intensity of a transverse wave. This will become a basic, this will help you even for sound chapter. There's a purely some sort of like conceptual and mass oriented. Next, reflection of a wave at closed end, like a wave propagating on a string when reflected by closed end, open end. Then refraction of wave, wave moves from one medium to another medium, the related concepts and formulas. Then standing waves on a string, very good concepts and formulas available here. Then sound wave propagation, the longitudinal wave propagation. Then expressing the sound wave, like how the parameters of medium will change. Then we are going to discuss the speed of sound. Then here the loudness, how to measure the amount of sound. Then we'll discuss the properties of the sound waves, like if the two sound signals undergo superposition, then we'll get the interference of sound wave, then the organ pipes, then the beats, then the Doppler effect. It's a lengthy, definitely you need lot of time. I'll try to cover in almost the least amount of time, minimum 2 hours needed. So you have to watch all this like a total video, learn it, recollect all the formulas, then solve PYQ. Then you can see the benefit of this particular waves and sound. Two questions for JEE Mains and easily 2 or 3 questions for JEE Advanced. Okay, well, I'll start the first. What is a wave? What do you mean by wave? A wave is a traveling disturbance that transports energy from one location to another. The material the energy travels through is the medium. The energy travels through the medium. The medium will not propagate. Only the wave energy will flow through the medium. The moment of energy is called as a propagation. Like this, we define the wave and the propagation. The flow of energy through a medium, what we can call that as a propagation or the wave propagation. Then what are the types of waves? Types of waves. So we have the mechanical waves, which require medium for its propagation. Then non-mechanical, electromagnetic waves, or we can also call this as non-mechanical waves. Which doesn't require medium for the wave to flow. So best example is the transverse waves or the light waves or what you can call EM waves. This we'll discuss in EM waves chapter. Our entire discussion will be waves and sound. Again, this mechanical waves which require medium are are classified into transverse waves and the longitudinal waves. So what are the transverse waves? Like a wave propagating on a string. Wave propagating on a string. Then what about the sound waves? The example of longitudinal mechanical wave is sound wave. Our entire syllabus, the first part will be waves, the second part will be sound wave. This is what we'll be discussing here. How do that transverse wave will propagate? How do that longitudinal transverse wave? So in case of the transverse wave, in case of the longitudinal wave, the particles of medium will move along x-axis and the energy will flow along x-axis. The energy will flow along x-axis and the particles of the medium also will flow along x-axis. Okay, this is what happens. So here it will flow in this direction. The particles of medium will propagate along x-axis and the energy also will flow along x-axis. In case of transverse wave, the energy is flowing along x-axis and the particles of medium will vibrate along y-axis here. This is like a rope. The particles of medium will be vibrating along y-axis here and the energy is flowing along x-axis. What is the longitudinal wave? The energy is flowing along the x-axis and the particles of medium also vibrate along x-axis. So there's one basic happens in case of longitudinal and transverse wave. In case of the longitudinal or the sound wave, the wave will propagate along x-axis and the particles of the medium will vibrate along x-axis. In case of the transverse wave, the wave will propagate along y-axis, x-axis, and the particles of the medium will vibrate along y-axis. So there's a basic idea of the longitudinal transverse wave, longitudinal mechanical wave. This particular thing we'll call this as a string or like a rope, anything you can call it. At t equal to time t, I see the disturbance is present here. Then the disturbance will take some time to propagate. Will take some time to propagate here. Then what is the equation? Equation of SHM will be y equal to a sine omega t. At time t, if the disturbance is here, when it would have started? It would have started earlier. At origin, it would have started earlier. So how much of time the disturbance will take to cover this distance? X. So this should be equal to how much here? The time taken by it to arrive here will be omega t minus x by v. What is x by v? Time taken for the disturbance to arrive here. So then this will become wave equation y equal to a sine omega t minus omega x by v, or this wave equation we can write it as kx. Then this will be written as, where the omega by v we can write it as k, where k is called as propagation constant, where we'll define one quantity called as wave speed, which is equal to coefficient of t by coefficient of x. Then this is wave speed v equal to minus omega. What is the coefficient of x will be omega by v, and coefficient of t is omega. Coefficient of x will be minus v. So like this, substituting, we'll get, substitute omega with sign. Coefficient of t is how much omega, coefficient of x is minus k. Then minus of minus will get this one. This is called like a wave speed. This is a symbol, or the speed with which the wave will propagate here. So there's one formula which you have to remember, very, very important here. This is a general wave equation we are discussing. What do you mean by A? A will become amplitude. What is omega? Omega equal to 2 pi f or 2 pi by t. Time taken for the point on a rope to complete one oscillation. There's the t. And there's the angular frequency. K is already a defined propagation constant. What is the v? Wave speed. What is the y? Y is the displacement of point on a rope. How do this particular wave propagation will occur? That let me show. Here for the wave to propagate, here point one end of the rope, I'll hold it. I'll move my hand up and down. Then a disturbance is set up and the wave starts propagating. Here, what is the direction in which the wave will propagate? The wave is going to propagate along x-axis here. The points on a rope, they'll be moving up and down. This was the transverse wave in a rope or transverse wave in a string. What is amplitude? This part will be amplitude. What is omega? Omega equal to 2 pi by t. What is capital T? Time taken by my hand to complete one oscillation, to and fro. Similarly, a point on a rope will execute SHM, will complete one oscillation. There's a time period. And what is the K? Propagation constant. Like this, a transverse wave is set up on a rope. How to produce a transverse wave? One end of the rope you connect to the wall, other end you move up and down. Then a transverse wave will be set up and it will move here. How the points on a rope? The points on a rope will move up and down. This is a basic idea of the transverse wave propagation, and this is called like a wave equation. Okay, now we'll differentiate this. Dy by dt. A omega cos omega t minus kx. This will become particle velocity. If you differentiate further, this is called as particle velocity. I'll differentiate this. Minus a omega square. So this will become acceleration minus omega square y. So this will be, so points on a rope, they'll execute SHM. Will move up and down. And how the wave will propagate. Points on a rope will execute SHM. So the points on a rope will execute SHM. And how the wave will propagate here. So there's one basic idea. What is this particle velocity? Particle velocity or velocity of a point on a rope. Velocity of a point on a rope. Okay, this is about the particle velocity. This is the acceleration of a point. This will be the displacement of a point. So how you measure y? Y will be this one. Then the point on a rope will be moving up, will be moving down, up or moving, will be moving up or down. So this will be moving down, this will be moving up. There's a particle velocity. It will have acceleration, it will have displacement, all those things. So then, so what do you mean by x? X is the position at a point, some distance, and what is the t? Instantaneous time. So these are all the basic things, sir. Okay, fine. No, this one, this will be a rope. At t equals 0, we have like this. Now how do they'll be moving, how the points on a rope will be moving. So for this we'll go back to the basics of mathematics. Omega t minus kx. I'll differentiate this. Dy by dt. A omega cos omega t minus kx. Then I'll differentiate with respect to x. This will become minus ak cos. So particle velocity is equal to minus, okay, I'll divide these two equations, dividing these two, Vp by dy by dx, this will become minus omega by k. What do you mean by omega by k? Will become wave speed. Wave speed, I'll use symbol. What is Vw? Means wave speed. Okay, fine. So this will become Vp equal to minus Vw dy by dx. What mean by dy by dx? Slope. So at t equals 0, how the points on a rope, they'll be moving here. So the wave is propagating in the direction. So these points are at test points A. So like the point behind D, they are at test. Then what is the slope here? Here the slope is negative, negative, positive. So the points on a rope here, they'll be moving up. And here slope is positive, velocity, wave is propagating along x-axis. So using this formula, these points, they'll be moving down. And this will be moving. This will be a test. This will be moving at t equals 0. After some time, this will come. This will be moving up. Will be here. This will be a. This will be a test. This will be moving down. This will be a test. This will be moving down. This will be moving up. This will be moving up. Fine. How the particles? Similarly, this will be moving up, moving up. This will be a test. Now point E will be a test. This point will be moving down. This will be moving down from this formula. Slope. What is the slope here? Positive. Slope positive. Wave velocity positive. Velocity of particle negative. Negative means downward. Velocity of particle. Here I'll indicate. This is the particle velocity. So this point will be moving. Okay, this will be moving up, moving up. This will be a test. This will be moving down. Like this, the points on a row. These are at mean portions. So I'll show for complete thing of these arrows. What are these arrows? Based on the formula, based on this formula, how the different points on a rope will be moving up and down, will be showing it. This is our basic understanding. Okay, like this. So points on a rope, they'll be executing SHM. This will be one oscillation. So the same point, if you check at this particular point, this will be, it has moved up, it has come to upper extreme, and then moving down, come to the, again at mean portion moving down, and reach a lower extreme at rest, again moving up and come to mean portion. This will complete one oscillation. This point will not move horizontally. This point on a rope will move vertically up and down. The wave will propagate along x-axis. You can see there was a one wave, now two waves are there. Like this, the wave propagation will take place. How the points on a rope? So you can, we can directly look at only this particular point. You'll get exact picture. How this point E? The point E is only moving along you can see that it is moving only along y-axis. This is one basic condition, very important. I'll okay, look at only this, at least yellow color strip, will get a basic picture. How the point E? The point E will move just vertically up and down, and the wave will propagate along x-axis. And this is called like amplitude, maximum displacement of a point. Hope everyone got the idea. Various forms. y equal to a sine omega t minus x by b. And here, what is the condition? The wave is propagating along x-axis, positive x-axis. If you write equation like this, then if you write equation y equal to then now the same wave now will be propagating along negative x-axis. Or what is the other equation? Other equation you can write it in this way also. Omega t minus kx, here a sine omega t plus kx. There's a wave equation. There's a generalized equation, or we can even write it in different way also. A sine omega what you can write 2 pi by capital T. This will be 2 pi x by lambda. What is the lambda? Lambda is the wavelength. This will become one wavelength. Or this will become wavelength. Agreed? These are the things which you have to remember. Next we have the two types here. Here called as wave speed. The speed with which the wave propagates is called as the wave speed. Next, the particle velocity. How the particle velocity? The particle velocity will be here in this direction. Okay, there are velocity of point on a rope will call particle velocity. The speed with which the energy will flow on a rope, that will call wave speed. Then as the wave propagates, so this particular thing, then what makes it to propagate? Because of the string taut. Then using this equation, then 2t sine theta, your component of this part here. This part, we are drawing it here. Then here tension T and T will act. This we are showing it. So 2t sine theta is equal to, this will provide required centripetal force. Where r is the radius of curvature. Then theta very small, or d theta will write it, no problem. D theta very small, sine d theta will become d theta. Delta m will become mu into delta s. What is the delta? dl, or nothing but dl, we can write it. Vw square by r. So this will become 2t d theta, mu dl will become r d theta. R2 d theta. So therefore the expression for this will be wave speed is given by this one. T by mu, where T is called as a tension in the string, mu is this one. What do you mean by T here? T stands for tension string. Mu will be mass per unit length. Mass per unit length of rope or string, or linear mass density. So it depends on the wave speed, depends on this quantity. It is depends on frequency, or it depends on the medium. The wave speed depends on medium and also stiffness of string. The wave velocity or the wave speed. There is one formula which you have to remember, very useful for you. Okay. At t equals 0, a pulse transfers, a wave pulse is set up. We have to calculate the time taken by the wave to move from lower to upper end. Then we know the formula, what is the wave speed equal to t by mu. Then what is the time it will take? At t equals 0, the pulse is here. Let m be the mass of this rope and L be the length. Let L be the length of it. Then I'll assume a small element. The mass of this element, let it be dm. Then it should be balanced by the tension. here T, here T. So the tension should be slightly more on upper end than the lower end. Let this be dx, let this be x. Then who will balance the weight of this small element? This additional tension dt. Then we'll write it here. dt is equal to dm into g. Mu dx into g. Mass of this small element mu dx. dt is equal to mu g dx. The tension 0 to x. So T is equal to mu gx. So this is the expression for tension at a distance x. Then the wave speed is given by T by mu gx by mu. It will cancel out. This is the wave speed. So as the wave propagates, its wavelength will increase. Now the wavelength of the same pulse, when it reaches the upper end, it will become broader. So here it's having wavelength lambda 1. Here how much it will have wavelength? Lambda 2. Here it will have speed v1. Here it will have speed v2. Then what will happen to frequency of the pulse? Will not change. Why the speed will change? Because the tension at upper end will be more than lower end. So and we know F equal to V by lambda. This is one basic equation. Try to remember. As the wave propagates, the frequency of wave remains same. Speed and wavelength will change. As the speed changes, wavelength will change. So then this will be dx by dt. Time taken by the pulse to propagate. This should be equal to root of gx. This will be x to power of minus 1 by 2. T equal to 0, this is time. So this will be x to power of minus 1 by 2. This will become 2 root x 0 to L, or there's a time taker. Okay, fine. Set t equals 0 here. After some time t, the pulse will be here. So this is about the time taken. The wave pulse will take some time to propagate. There's one generalized things I'm discussing. You have to remember this formula. Then similarly, which we have the wave propagating on a rotating ring. When a ring rotates about an axis passing through center perpendicular to plane. So what is the expression for tension? Tension is given by lambda omega square r square, where lambda is mass per unit length. This is the expression for tension. On this particular thing, the wave will propagate. Then velocity of wave with respect to rope or with respect to ring equal to velocity of wave minus velocity of ring. This is a formula. Then what is the velocity of wave with respect to, what is the velocity of the rope? Velocity of the rope is r omega. Then we have to use this formula. Velocity of the wave with respect to rope equal to tension. So I'll use formula. Velocity of the wave, it depends upon tension and the linear mass density. Okay, I get this. So what we calculate here, this will become velocity of wave with respect to rope. And what is the tension in the rotating ring? Lambda omega square r square. This lambda. This will become r omega. What is the velocity of the ring? Tangential velocity will be r omega. Then I'll substitute here r omega minus this will be r omega. Velocity of wave with respect to ground will be 2r omega. There's the same thing. So there's a one vector equation. Try to remember. Velocity of wave with respect to medium equal to velocity of wave with respect to ground minus velocity of medium. Next one we have the phase of a wave. What do you mean by phase of a wave? So there's two different things are there. So what is a y equal to what is y is equal to a sine kx minus omega. What is actually meaning of this? Like, so here if you look at the representation of a wave, how the wave will be put t equals 0, at t equals 0 x equal to 0. What is the condition? At t equals 0 we'll plot this graph. This graph, how it will be? It will going to be like this. Then we'll also differentiate this. This will become minus a omega cos kx minus omega t. Then this is y, this x, this is x equal to 0 point. At t equals 0, at t equals 0, then put t equals 0, then it will have the negative velocity. How this particular point will be moving in this direction. And these points on a row will be moving up. Okay, fine, like this. So there's a meaning of y equal to a sine kx omega. How the wave is propagating along this direction. And what is Vp? Vp is what called as particle velocity. And the point at x equals 0 should be moving downward. Then you should write, means at t equals 0, if the point at x equals 0 moving down and the wave is propagating along x-axis, you have to use equation. Similarly, no, if y equal to a sine omega t minus k, what actually meaning of this one? At t equals 0, we'll substitute, we'll get y equal to minus a sine kx, so how the curve will be? The curve, the shape of the row will be like this. Then how the wave is propagating still along x-axis. Then you put t equals 0. At t equals 0, x equals 0, this will be, velocity will be maximum and positive and will be moving up. This will be moving up. This is the meaning of this one. The wave, in both the cases, the wave will propagate along positive x-axis. And this will be the shape of the row. At t equals 0, if the shape of the row is like this, and at x equals 0, the particle moving up, you have to write in this way. Similarly, we'll take the one more. Y equal to a cos kx minus 1. What is the meaning of this one? We'll differentiate this. I'll get this as a omega sine kx minus omega t. Differentiating, we'll get this one. Put t equals 0, x equals 0, the particle will be at rest. It should be at mean position. Then upper or lower mean position. Put t equals 0, at x equals 0, the particle should have y displacement plus a. And how the wave is propagating along positive x-axis. Then all these points on a rope will be moving in this direction at this instant. This is the meaning of this. This is what we'll call the phase angle. This is having a phase angle of pi by 2. Next we have like this. This everything, what is this? This is a rope. Then what is the meaning of this one? So this will be equal to, like a put y equal to a sine kx minus omega t plus y. At t equals 0, this is the shape of the rope. Put t equals 0. A sine k0 minus omega 0. The initial phase angle we don't know. What is the value of y? Y is a by 2. Then if you solve this, we'll get 1 by 2 equal to sine pi. So this is equal to pi by 6. This is the initial phase angle. So then the equation will be y equal to a sine kx minus omega t plus pi by 6. Like this is called the phase of a wave. Just remember, simple idea this one. You don't get any complicated things. Just a small idea is needed. What do you mean by phase? At t equals 0, at x equals 0, where the particle is. Is it mean portion moving up, mean portion moving down, or at upper extreme, or in between moving down? So how it is? It is moving down. This is called like a phase of a wave. At t equals 0, I'm showing. So what is this? This is a rope, or you can call medium. What are the formulas we have? Minus wave speed into dy by dx. Then we'll calculate the slope. Here, what is the slope? Slope is positive. Wave propagating along x-axis positive. So particle velocity negative. How these points on a rope? They'll be moving down. Here slope is negative. Negative of negative. This is positive. Wave velocity positive. So I'll get positive. Okay, these are the points which will be at rest. Then look at the phase of these two. These two are having same phase, no? Both are at mean position moving down. So the distance between 2 points on a rope which will have same phase is called as a wavelength, or this is called like a wavelength, and where k equal to 2 pi by lambda. And here if I give the angle, if I draw a tangent, and if I give the angle, then what is the velocity of point P? Velocity of point P equal to wave speed into dy by dx will be tan theta. If you know the angle made by the tangent at that particular point on a rope, if you know the theta, tan theta, and if you know the wave velocity, we can get particle velocity, or if you know the particle velocity, we get the wave speed. And this particular thing will become amplitude. Okay, and what is the wave equation? Wave equation will be y equal to a sine kx minus omega t. These are all the basic things. Then we have the formula. The phase difference between any 2 points on a rope is given by this one. You can calculate the phase difference between this point and this point, between these 2 points, between 1 and 2. What is the distance between them? Delta x, you can calculate horizontal distance. Substitute here. Then we'll get the phase difference between 2 points on a rope. Similarly, so what is y-x graph? Y-x graph it gives shape of rope at time t. What all you can find out from y-x graph? Amplitude, particle velocity, wave speed, the phase difference, and the wavelength. All these things you can find out by using y-x graph. Similarly, we are having one more called as a yt graph. What is yt graph? It gives displacement of a point in a rope varying with the time when wave is propagating. Then time taken by the wave to complete one point on a rope, one oscillation. So from yt graph, what we'll get? Of a point on a rope, only one point on a rope, how its y displacement varies with the time is available. From yt graph, what we can calculate? Time period. If you know the time period, you can calculate frequency, and you know omega. So these things you can calculate from yt graph, and you can calculate also the amplitude. So all these quantities are available in the yt graph, displacement versus time graph. Okay, fine. After getting this, then can you calculate the phase difference of a given point at various interval of time? This is a formula. At t equal to 1 second, at t equal to 3 seconds. Between this interval of time, how much of phase change it has undergone? Okay, this is a formula. Okay, kids, all these things you have to remember. Next year. So when a transverse wave propagates on a rope, then the wave velocity will be in this direction. Points on a rope, how they'll be moving up. So according to this condition, so here we will bring the mean position. Then how the various points on a rope, they'll be moving in this direction. Okay, I agree this. Then if a point is moving on a rope, definitely it will have the kinetic energy. Definitely it will possess the potential energy. So then the kinetic energy of that small element is given by dq is equal to dm vp square by 2. And we know y equal to a sine omega t minus kx dy by dt, or particle velocity, is given by a omega cos omega t minus kx. Similarly, dy by dx slope is equal to minus ak cos omega t minus kx. Like that, a given point on a rope will possess both kinetic energy and potential energy. Why potential energy? Because it gets stretched. So there is a stretched rope. It is not at natural end. So it will possess both potential and kinetic energy. So how to express that potential energy and kinetic energy? So we have directly similarly the potential energy you can determine. The potential energy of small element is given by T into elongation. If you look at this small element, it will get elongated when its length will be delta x. When the wave propagates, its length will become delta L, say delta R, and because of this it gets stretched. So what is the delta L equal to delta R minus delta x. So like this, the element on a rope will get stretched. Because of that, it will possess the potential energy. Then we'll use the formula wave speed equal to under root of T by mu. Using all these formulas, we'll end up with one basic. The potential energy or kinetic energy is given by tension T2, slope into length of that element. So what is the meaning of this? Meaning of this, if there's a rope, here if the wave is propagating and the shape of the rope will be like a sine wave. Then here we have chosen dx, this element. It will have tension T. It will have speed v. Then it will make a slope dy by dx. Then length of the rope, when no wave propagating, it was dx. It will possess both potential as well as kinetic, is given by this particular thing. Then like this, if you integrate everything, the potential, the energy, the total energy will be sum of potential plus kinetic. So potential energy and kinetic energy, how much is equal to? U equal to rho omega square a square by 4. Same thing, kinetic energy. Per unit volume, the total energy density will be, all these are energy density. Kinetic energy per unit volume, potential energy per unit volume. This should be equal to how much? Rho omega square a square by 4 plus rho omega square a square by 4. Then the total energy density is equal to energy density into volume of a rope. What is the energy density formula? Rho omega square a square by 2. Volume of a rope will be length, or say x length, into area of cross section. So the total energy of the wave will be rho omega square a square s x by 2. Rho into s will become mu omega square a square x by 2. Then we'll define average power, energy flowing per unit time, mu omega square a square to x by delta, which is equal to mu omega square a square by 2 wave speed. Then we'll define the intensity of a wave. The intensity of a wave is given by energy flowing per unit area per unit time. Per unit area per unit time. So this will become rho omega square a square s x by s delta. S will cancel out. Rho omega square a square vw by 2. like this will become the intensity of a wave. This is called like a average power. This is the energy of a wave. When a wave propagating on a rope, transverse wave propagating on a rope, potential energy and kinetic energy will be in equal proportion. And where both will be maximum here, both will be maximum here at mean portion. Both kinetic energy and potential maximum, both will be minimum at where it will be, there will be minimum or zero at extreme point. And as you move from mean to extreme, potential energy and kinetic energy both will decrease. And both will be in equal proportion. The total energy on a rope should be equal to sum of potential plus kinetic, and both will be in equal proportion. Okay, this overall the transverse wave propagation you are supposed to remember like this. We got expression for intensity of wave, power of a wave, energy of a wave. Then it depends on length of the rope. Then when the transverse wave propagates, where the potential energy kinetic energy maximum at mean portion, and both will be minimum at extreme point. And as you move from mean to extreme, both will decrease. Potential energy and kinetic energy will decrease. Agreed? Next we have the pulse wave propagation. So there's a rope itself. What is this? There's a rope itself. Then there's the equation. So yeah, I'll take the quotient of t by quotient of x. What the formula will be? Quotient of t will be minus v. Quotient of x will be plus 1. And there's a wave speed. And in what direction the wave is propagating? Along positive x-axis. Then what is the amplitude of wave? Put x equals 0, t equals 0. The amplitude of wave will be given by a by b. Then at t equals 0, put t equals 0. The wave equation will be a plus bx whole square. And as you vary x, we'll get the shape of the pulse. Here the points on a rope here will be moving up like this. Any reason for that? The formula will be Vp equal to minus V into dy by dx, the slope. Like this, we can calculate velocity of any point on a rope. How the shape of the rope will be? Like a pulse. If you give one jerk, it will propagate here. So a rough diagram. How the pulse will be here. After some time will be here. After some time will be here. Like this, the pulse will be propagating. This is called like a pulse wave propagation. How to calculate its amplitude? Put x equals 0, t equals 0, what we get maximum value of y, that is the amplitude. This will become amplitude. And how to calculate velocity of any point when pulse propagating? Again the same formula. Differentiating, then at x equals 0, t equals 0, use this particular formula, you can calculate velocity of any point on a rope. Okay? No. As the pulse starts propagating, so here we going to discuss the reflection of a wave on a string at the rigid end or wall. This particular thing, when a pulse arrives here, get reflected, then will get inverted. So here what is the incident wave? The incident wave is y equal to a sine omega t minus kx. Let's assume that one. After reflection, the direction of wave propagation changes. yr equal to a sine omega t minus k, this will be minus x plus pi. Y plus pi get inverted. So this will become a sine omega t plus kx plus pi. This will be reflected wave. This is yr, this is incident wave. So when a wave reflected by a wall, it will undergo phase change of pi radian, will get inverted. This is, if it is erect, this will be inverted. Okay, here this is yr, this yi. So you have to remember, now the total energy will be only kinetic. Here it is having both potential plus kinetic. Here potential plus kinetic. At one instant it will have only kinetic energy, no potential energy. Again the same energy it will get back. So when a wave reflected by a rigid end, it get reflected, will get inverted. It start moving in opposite direction. So there's a basic formula. Then sine omega t, so the equation will be further omega t plus kx. So similarly, we'll go for reflection at the free end. Reflection of a wave at the free end. So there's a wave propagating along positive x-axis. Then what is the incident wave? Y equal to a sine omega t minus kx. This is a yi. The wave is propagating in this direction. It gets reflected and will not get inverted, but it will change the direction of propagation. Now the same wave is moving towards left. Then the reflected wave is given by a sine omega t will not get inverted. So there's a basic idea. This will be yr, this will be yi. So there's a one basic, there's a physical diagram, there's a mathematically you should write, because y minus x, because the wave starts propagating towards negative x-axis, so minus x you have to write it. No sir, what about the different shaped things if they are incident? A generalized equation. So you can see there's a curved part of the rope. If it is getting reflected, then I will manage here. Then we know first which part of the pulse this will get reflected. So the drawing curve, this will be inverted. First it will go in inverted. So it will be like this. Then I'll show it clearly. Okay, this will be. Okay, after reflection, this will, so this is the will give a number. 1, 2, 3, 4, 5. Here the number will be like this: 1, 2, 3, 4, 5. This is a reflected wave. Fine. First segment 1, 2 will get reflected. So 1, 2 will return back first. And there's a basic idea of how to draw the reflected wave when it reflected at the rigid end or wall. No, there's a reflection at the free end. 1, 2, 3, 4, 5. Then will not get inverted. Will not get inverted. That's all here. So it will be vertical line here. Then it will be. I'll extend this line also. There's a point P. Now where are 1, 2, 3? So this will be 1, 2, 3, 4, 5. Just through diagram base also you can remember. Will not get inverted in case of reflection at the free end. Reflection at the rigid end will get inverted. So here reflection at rigid end. This is reflection at free end. And what is this? There is a rope. Don't assume anything. The energy on a rope is flowing, so therefore the shape of the rope will be like this. In a very simplified way I am explaining here. So you must be able to remember this one. This is very, very important. Now we have there's a rope, there's a pulse. It is approaching the fixed end. This will be a fixed end. Then you can see here. Now it will get inverted. Again I'll repeat it. The wave gets reflected, will be inverted. This process will continuously I'll be sending incident waves, consistently reflected waves. There's a reflection at the rigid end. Similarly we'll go for free end. If a wave is incident at the free end, It'll get reflected and returns back. There won't be inversion. There won't be inversion. Will get reflected back. So there's an incident, will get reflected and returns back. So there's one basic idea. Okay, kids, like I shown some animations also. This will be some type of questions what you get in exam. You should be careful. I just took the curved triangle and the square waveform. I think I'm showing this reflection at both the rigid end as well as free end. Okay, we'll discuss the superposition of waves on a string. So this dotted one is a string or rope. There's a pulse 1, there's a pulse 2, both are moving, they're approaching each other. Now this will be the resultant shape of the rope. The shape of the rope will be like this. Earlier this is the shape of the rope. No, this black line I'm drawing is a rope itself. Now next part, the shape of the rope will be like this. Okay, both will undergo superposition and they'll pass through each other as if other is not present. This is the possible ways in which they'll undergo superposition. There's one small thing which you have to remember, very, very important. This will be the possible shape of the rope. Why it will undergo superposition? So that practically only this is applicable. So why can't a yellow color pulse climb on the blue color pulse? That particular pulse is practically not possible. So the superposition will occur like this only. Here, there's a pulse 1, there's a pulse 2, they're approaching. Now there's a pulse 1, it is going to move like this. There's a pulse 2, it will be moving towards left. Now both will undergo superposition. We'll see what will happen to that. Now they'll undergo superposition. Here it will be like this. Superposition. No, there's a pulse 1, let's assume. There's a pulse 2. They'll approach each other. They're approaching. They're approaching. Now they'll undergo superposition. They'll cross each other like this. Like this continuously will making them to undergo superposition. This is one basic idea of the superposition take place. Then what is the displacement of this point? You check it here. The displacement of this point you can see now it will become. So what is the displacement of any point on a rope? Sum of displacement due to individual waves. Agreed? So there's one basic method. Now I have this one triangular pulse. This is a square pulse. Here we'll make them to undergo superposition. Now as they approach each other, the superposition will take place. Will be like this. Below you can see these are the pulses undergoing super. Below is what? The resultant. This will be resultant. You can see clearly. Now they are undergoing superposition. This will be the shape of the curve at one instant. Next instant it will be like this. So this is the square pulse, this is a triangular pulse. Then again you can see superposition. Resultant pulse. Right? So these are some general ideas which you can develop. And I'll change the shape of the pulse. If they are undergoing, like this is a square pulse, this is some triangular pulse. Let them undergo superposition. Below is what the resultant. This will be the shape of the rope. This will become shape of the rope. Okay, fine. I'll show it again here. They are approaching each other. No, this will be the shape of the rope. So I'll change it if it is like this. They're going to approach each other. The resultant pulse will be at one instant will be like this again. Okay, fine. So these are the ways in which you should understand things. Next topic will be refraction of a wave on a string. The wave is moving from denser to rarer medium. Let the refractive index, so like this one, the mass density of this linear mass density be mu1, let this be mu2. And let the tension in the rope, let it be T. Here the wave pulse will have speed v2. So what is v1? v1 will be T by mu1. What about v2? v2 equal to T by mu2. Since mu2 less than mu1, so v2 greater than v1. So the wave will propagate with more speed in the rarer medium. If a pulse approaches a boundary, this is called like a boundary. This is called like a boundary. Boundary means this is a denser rope, this is a rarer rope. The linear mass density of this rope will be more than this one. If a pulse approaches, a part of it will be reflected, a part will be transmitted. Then if AR is if this is the amplitude of incident pulse, this will be amplitude of transmitted pulse. This will be amplitude of reflected pulse. So what is AR equal to V2 minus V1 by AI V2 plus V1. What about amplitude of transmitted pulse? Amplitude of transmitted pulse is given by V2 plus V1. Okay, fine. So the wave will get reflected. If this is the incident wave, y equal to a sine omega t minus k1x, AI. Yeah? Then what is the transmitted pulse will be at sine omega t minus k2x. It is in different medium. Then the reflected pulse is given by minus AR sine omega t plus k1x. Y plus is the reflected pulse. This is the incident pulse. This is a transmitted pulse. Y k2 different medium. Same medium, speed will not change. The amplitude of reflected is given by this particular form. Amplitude of transmitted by this form. Similarly, when the wave moves from denser to rarer, when the wave moves from rarer to denser, this is what happens. So here this is the rarer medium, this is a denser medium. So here refractive index mu1 you call, so like a linear mass density mu1, linear mass density mu2, mu2 greater than mu1. Then v1 equal to T by mu1, v2 equal to T by mu2. So here mu2 greater than mu1, v1 greater than v2 less than v1. Here the wave will move with more speed here than this one. Okay, there's amplitude of incident pulse. The same formulas, huh? There's amplitude of reflected pulse. The reflected pulse will not, and this is transmitted. And this is incident. Then what is the equation for incident pulse? Incident pulse is given by AI the reflected pulse YR equal to AR sine omega t plus K1x. Transmitted pulse YT is equal to AT sine omega t minus K2x. The reflected pulse will not undergo phase change of pi radian. There's a formula. So whenever you move from rare to denser medium, the reflected pulse will not undergo phase change. Transmitted pulse will not undergo phase change. And the speed of the transmitted pulse will change because it is in now different medium. And the amplitude of reflected transmitted already a given equation. There's a one basic conditions which you have to remember. Next part we'll be discussing standing waves on a string. Here I'll send the incident wave. It goes and gets reflected. Okay, fine. And this is a rope. Like this, they'll undergo the superposition. Then if they undergo superposition, what do we get? It may undergo superposition in other way also. So if the wave goes, it gets reflected by a rigid end. The reflector will get inverted, they'll undergo superposition. If the wave is incident, it gets reflected by a free end. And the pulse open will remain erect. And these two will undergo superposition. Then we have to see that how the resultant wave will be formed. Then we have to write down the equation for wave. Then we know incident wave is given by, here I'll write for this, yi is equal to, the resultant wave is given by yi plus yr. What is the incident wave? A sine omega t minus kx. The reflected wave is given by a sine omega t plus kx. 2a sine kx cos omega t. Like this, we'll get the equation for standing wave. They'll undergo. So similarly here, what about yi? This will be a sine omega t minus kx, a sine omega t plus k. Why plus kx? Because reflected is moving towards left. The superposition of this will lead to, when the two waves, if they are, one is erect, this pulse will get reflected by rigid end, will get inverted. When they'll undergo superposition, we'll get the equation like this, sine kx cos omega t. Similarly, if this wave will get reflected by free end, it will not get inverted. If they undergo superposition, then we'll get equation. Both these are called as a standing waves. Both these are called as standing wave. And what is the amplitude of standing wave? Twice the amplitude of traveling wave. This is called like a traveling wave. This is a traveling wave. This is a traveling wave. This is this one, traveling wave. So, and how do the standing wave? The standing wave formed will be of like this. Then what about here? Here it will be formed like this. This will be the standing wave. Let me draw it clearly. Okay, this will be the standing wave. Okay, when two traveling waves moving of same speed, same frequency, moving opposite to each other, undergo superposition, we'll get the traveling. We'll get a standing waves. And what is the amplitude of standing wave? Twice the amplitude of traveling wave. Then here we'll define the some quantities called like a nodes, antinodes. So what are the nodes? Nodes are the points which will be always at rest. First we'll define the quantities. So I'll take help of this one. 2a sine kx cos omega t. What about nodes? Nodes are the points which will be always at rest. For this to happen, sine kx should be equal to 0. Then kx should be equal to how much? 2n pi. Then k equal to 2 pi by lambda, or x equal to n lambda. So what are the positions at which you can find out the nodes? 0, n pi, this will be n pi, n lambda by 2, 0, lambda by 2, lambda, 3 lambda by 2, 2 lambda, and so on. So which will not vibrate. Next we have antinodes whose displacement can be maximum. How much maximum? Equal to plus or minus 2a. For this to happen, sine kx should be equal to plus or minus 1. Then kx should be equal to 2n minus 1 pi by 2. K equal to 2 pi by lambda. So x equal to 2n minus 1 lambda by 4. Position of antinodes will be lambda by 4, 3 lambda by 4, 5 lambda by 4, 7 lambda by 4. Now, what are antinodes? Which will vibrate. Which will with amplitude 2a. Then how to calculate the position of the maximum amplitude of any point? 2a sine kx. So 2a sine. What is the value of k? 2 pi by lambda. Like this you can calculate the amplitude of any point on a rope. So when a standing waves are set up, what conditions will come? We'll get the loop will be of like this. So why you are drawing loop? Yes, when standing waves are set up, the string will vibrate at higher frequency. It will get, for us, it will get visible like a loop itself here. Okay, fine. So these are the, so what are the equations we have? Y equal to 2a sine kx cos omega t. When standing wave set up, you can find out the displacement of any point using this formula. If you want velocity, 2a minus 2a omega sine kx sine omega t. For acceleration, it will be minus omega square y. Then dy by dx, slope will be 2ak cos kx cos omega t. Like that we can calculate the slope also. So this is a rope itself. The rope itself will appear like a loops. The number of loop depends upon the frequency. Then we'll discuss the normal modes on a string. The normal modes on a string. The string is connected at this particular point. We know this should be a node. This should be a node, and this is string, a rope or a string. The midpoint, I'll hold at midpoint, I'll pull it down, it'll start oscillating. Then what is the total length of the rope? Length of the rope is L. Then the wavelength will be, it is the first mode, this is called like a first harmonic. Or fundamental tone. So what is the length? Length will become L1 equal to length of the rope, L equal to lambda 1 by 2. What is lambda 1? Further V by 2 F1. So F1 equal to how much? V by 2L. Similarly, at the midpoint, at 1/4 of the rope, I will displace the string. I'll pull it down and release. Then 2 loops will be set up. Then this we know antinode. Here antinode, antinode, node, node, and node. Then here wavelength lambda 2 by 2, lambda 2 by 2. The length is equal to lambda 2. What is lambda 2? V by F2. What is F2 equal to? V by L. Or this will become 2V by 2L. Frequency. Then this is called like a second harmonic or first overtone. Then at 1/3 of the string I'll strike it. Then we'll get the 3 loops. So then what is the total length of the rope is equal to lambda 3 by 2. Solve it. F3 equal to 3V by 2L. Like this. If there are n, this is called like a third harmonic or second overtone. Fourth harmonic. Or this is called like a third overtone. Then lambda L is equal to how much? 2 lambda 4. So F4 equal to 4V by 2L. Like that, nth harmonic frequency is given by this formula. So what is the total length of the rope? Should be equal to n into lambda n by 2. A generalized formula. Then the resonant frequency nth harmonic is given by this one. Then if E1 is energy in the first harmonic, then energy in the nth harmonic is given by the formula En equal to n square E1. These are the harmonic frequencies with which the string will be vibrating. Of the string, if you take the tuning fork and if you keep this tuning fork at the midpoint of the wire, then it's going to vibrate in the first harmonic. So what is the frequency of this tuning fork? F1 equal to V by 2L. If you take another tuning fork of frequency F2, if you keep this at the 1/4 of the length of the loop, then this will become F2 equal to V by L. If you keep the tuning fork of frequency F3 at the how much? 1/6, then we'll be vibrating. Then we'll get F3 equal to 3V by 2L. Like that we can make the string to vibrate a 1/4. So where you have to keep it the tuning fork at half of the length L by 2, next L by 4, next L by 6, next it will be L by 8. At these particular positions, if you keep the tuning fork, then the particular wire string is going to vibrate with a different resonant frequencies. This is actually basic meaning of this one. Now we can see here the resonant frequencies. I'll adjust the frequency at higher frequencies. You can clearly see the standing wave setup. At higher frequency, the string will appear like a loop. This will be vibrating. We'll determine the tension, the load suspended here. The string will have linear mass density and the tension also we can separate. And we will vibrate. The frequency of tuning fork we can adjust here at lower frequencies. We can adjust the frequency of the tuning fork also. So there's a vibrating frequency 125 Hz. So by changing the tension, other things, we can control this particular number of loops. So this is what the string will vibrate like this, and here is what the standing waves are set up here. Okay, fine. There's a one basic simple simulation I'm showing it. Next we have the experiment called as a sonometer. So from the basic equation, this F equal to NV by 2L, resonant frequency and nth harmonic. Further, this V, what is the speed of the wave given by T by mu, where T will become tension. The tension depends upon the what load we suspend here. and the same tension is set up here in the rope. And the rope will have linear mass density mu, and L is the length. By moving these bridges, we can adjust the length here. So first, how the square root of tension sinks. So the resonance frequency is directly proportional to square root of frequency. F1 by root T1 equal to F2 by root T2. How to vary the tension? By changing this load. The tuning fork will remain by varying the frequency. L will be constant. So as you change the load, corresponding tuning fork you can bring it and you can change it. So here what the F frequency. And at what frequency the tuning fork is vibrating, at the same frequency the wire will vibrate. This is called like a stem of tuning fork. They should come in contact with this wire. So at what frequency the wire will vibrate here, with the same frequency here the standing waves are set up between these two bridges. Okay, this one, the square root of tension of the string. The frequency is proportional to. The frequency is reciprocal of square root of linear density of the string. Is telling that it's proportional to mu. So F1 root mu1 equal to F2 root mu2. By changing linear mass density of the rope, we can make the standing wave to vibrate at different frequencies. Then it is directly proportional, it is inversely proportional to length of string. F1 L1 equal to F2 L2. How to change the length? By moving these bridges. Suppose I know the tuning fork whose frequency is F1. I'll adjust the length of the bridges L1. Then I will bring another tuning fork whose frequency I don't know. Then I'll adjust the length between the bridges so that number of loops are produced. Same number of loops are produced. Then I can find out the unknown thing F2. So what is this entire sonometer experiment? It is used to measure the density of substance and to find out the frequency of a given tuning fork. These are called as a sonometer experiment. Okay, kids. Next topic we have the sound wave propagation. Okay, what is the sound wave propagation? Is a longitudinal, the speaker. There's in general speakers, loudspeaker. There's a loudspeaker which will produce sound signal. The sound signal will propagate in this direction. And the particles of the air particles, they'll be vibrating. Then when they're vibrating, then at one region we'll get the compression, rarefaction. Compression means where the distributing particles will be very less. Rarefaction means the distributing particles will be more. Like that, the sound what happen will propagate in the form of like a compression and rarefaction. So this is the one basic methodology of the sound wave propagation. And how the particles, the particles will vibrate like this. They'll enter into the air. So this particular vibrations, when they enter into air, we can feel the sound sensation. No, how the longitudinal wave will propagate here. The particles of medium will be vibrating here. They'll vibrate along the direction of wave propagation. Then when they're vibrating, the distance between two layers will increase, the distance between two layers will decrease. That will lead to compression and rarefaction. So here, how the sound wave is propagating towards right. Then the layers there, they'll be executing SHM. You can see this red color layer. So it will be there only, will be executing here. You can select and all. The layer will be executing SHM. The layers they'll execute SHM and will get a compression and the rarefaction. Here you can see clearly once again. The wave will propagate towards right and the layers will be executing SHM. And the layers will execute SHM above their mean portion. Fine. We'll take the. Now this tuning fork will vibrate. As it vibrates, it will displace the particle. and due to that what happen, a rarefaction, compression, rarefaction is set up. What about the pressure at the compression will be maximum? The pressure at compression will be maximum, and the pressure at the rarefaction will be minimum. So here you can see clearly the compression, the propagation of a sound. Here the particles, they'll be vibrating. And this is about the pressure variation, and this is about the graph as a function of x it is. Then here it's a compression, maximum pressure. Rarefaction, the pressure will be minimum. Like that, where the compression, the pressure will be maximum. Where it's like a rarefaction, the pressure will be minimum. And the pressure, what happen, will vary. And how do this pressure will vary? So then this whole equation, you can write it like this: a cos kx minus omega t. Then what about the pressure wave? If there's a displacement wave, the pressure wave, excess pressure wave is given by minus dy by dx. This is equal to BAK sine kx minus omega t. So this will become pressure amplitude. So this is called like a displacement wave, where A is called as displacement amplitude. So when sound wave propagates, the particles of medium will exude SHM above their mean portion. And because of that, the pressure of medium will vary. So here it will be like a compression and rarefaction. Now, what is the pressure wave? What is the here like a proportional? I'll write it. So what is the equation we are having? Cos. Then what about the displacement wave? To get this cos wave, then this should be sine omega t minus kx. Then if you differentiate, what do we get? We'll get the cos. Then what is the equation? If I further extend this, so this will be the displacement wave. Put t equal to 0, so we'll get the displacement wave. This is the displacement wave. This is the pressure wave. Like this, they'll be related. So when a sound wave propagates through a medium and it is propagating in this direction. Now this is one basic generalized thing. Now we'll further explore this. Here we are having there's a displacement wave. There's a pressure wave. How the various particles will be moving. What is the equation for the pressure displacement wave? Given by minus a cos kx minus omega t. I'll differentiate this. Minus dy by dx. This will become minus bak. Derivative of cos will be minus, so this will become minus sine kx minus omega t. So this equation is what we have plotted. This is nothing but the pressure, excess pressure. The pressure at any point is given by P naught plus delta P. BAK will become amplitude. So this is a displacement wave, and this will be the pressure wave. Then what do we mean by compression? This will be the compression. Compression means this is a maximum compression. Here it will be maximum compression. Sorry, maximum rarefaction. What is the maximum? Where pressure is maximum. Here this will be maximum compression. What do you mean by compression? Where the pressure is more than P naught, that will become compression. So this everything is compression. This everything will be rarefaction. Okay, clear this one. So what is all where the pressure is less than P naught, rarefaction, where pressure is more than P naught, that will be the compression. So, and this layer will have maximum compression. So all these layers will undergo the compression. So suppose we'll give number, we'll give number will give 1, directly we'll give number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, these are the layers. No, which all having compression. Those layers where pressure is more than P naught. 6, 7, 8 are the compression. This everything is compression. Again here 14, 15, 16. Rarefaction will be 2, 3, 4. Rarefaction will be 2, 3, 4. Then next again 11, 10, 11, 12. All these are rarefaction. Okay, fine. Which are at upper extreme or right extreme, better select it. Which are at mean position. First we'll check it. Mean position. Mean position means 3, 7, 11, 15. Okay, fine. They are at mean position and they'll have maximum speed. And what about the maximum compression? Maximum compression will be maximum compression will be 3, next again 11. Maximum rarefaction. Maximum rarefaction. So maximum 311 will be maximum rarefaction. Maximum rarefaction. 5, okay, this one 7 and 15 will be maximum compression. Maximum compression, maximum rarefaction, and these are the rarefaction which are at right extreme. Those which are at 5 and 13, which are at left extreme. The one which are left extreme 1, 9, 17. Okay, fine. So these are the which are having maximum speed. The one. So where the speed will be maximum at mean position only, and where the potential energy maximum, where the pressure maximum, potential energy maximum, change in pressure maximum. So therefore, when a sound wave propagates, where the energy will be maximum at mean position only, or the layer which is having maximum compression will have maximum kinetic energy. The layer which is having maximum rarefaction will have maximum kinetic energy and maximum potential energy. Here at mean position, it will be U max, K max, U max, K max. So like this. In displacement graph, so when you are going for displacement graph, displacement wave, at mean position, potential energy, kinetic energy will be maximum. in the pressure wave, when you plot the pressure wave, at extreme point the potential and kinetic will be maximum. Extreme point in the sense compression, and where maximum compression refraction, there kinetic energy will be maximum. And how to predict the layers which are moving? Use this particular formula, dy by dx. We can tell in which layers are in what direction they are moving. And the wave is propagating along positive x-axis. This is one basic idea of the sound wave propagation. When a sound wave propagates, the layers will exhibit SHM given by this particular formula. The pressure of a medium or the density of medium varies, that is given by this formula. This is what the basic characteristics, and we just show compression, rarefaction. This everything is rarefaction, this is a compression, rarefaction. So similarly here, rarefaction, compression, rarefaction, compression. The sound wave will be categorized, and here this will be maximum rarefaction. So when you plot this, okay, if you want to show this one here, this everything is rarefaction. This everything, this will become compression. This will be the compression, and this will be maximum rarefaction. This will be maximum compression. This you can call it as rarefaction. Now again rarefaction, again compression. So this is one basic learning is what you have to do it. Okay, this. Hope everyone able to understand now. All these layers will have rarefaction. Among them, there will be one layer which will have maximum rarefaction. Similarly, all these layers will have compression. And there will be one layer which will have maximum compression. And if you know the displacement wave, you can calculate the pressure wave. From the pressure wave, the density wave. Here only I'll write it. What is the expression for density wave will be? Rho AK, rho naught AK, sine kx minus omega t. This is a density wave, pressure wave, this is a displacement wave. Now as the sound wave propagates, the speed of sound is given by b by rho. From the wave equation, b by rho will get it. Then what is b? B is a bulk modulus. Then we know the air present here will undergo isothermal process. Means here when the wave propagates, when the sound wave propagates, this is the compression. First this will be the normal. When a sound wave propagates through a medium, I am assuming some volume of air which will undergo compression, rarefaction. Initially let the pressure be P naught, density rho naught. It will undergo compression. This will be compression. This will be rarefaction. And again, this will be compression. Like this, the air which is present will undergo compression, rarefaction. Then the speed of sound wave is given by this one. So what about the air? The air will undergo thermodynamic process. What thermodynamic process? Let's assume that Newton assumed that it will undergo isothermal process. Newton assumed that it will undergo isothermal process. So PV is equal to constant. Then P dV plus V dP equal to 0. Then we can define this dP as P is equal to dP by dV by V. From the elasticity, this should become equal to bulk modulus. So therefore, now I'll replace this pressure of air by bulk modulus by the pressure of air. where P will become mean atmospheric pressure, rho will become mean atmospheric density. Mean atmospheric pressure and rho will become mean atmospheric density. So when we calculate, practically the speed of sound is 340. This is coming around 310. But practically how much it is speed of sound? 340 meters. There was some difference. So Newton just left it here. He assumed that this particular thing will undergo isothermal. Later the Laplace came. He assumed that the air, when sound wave propagates, the air will undergo adiabatic process. In adiabatic process, PV gamma equal to constant. Then P gamma V gamma minus 1 dV plus V gamma dP equal to 0. Then gamma P is equal to minus dP by dV by V. From elasticity bulk modulus, this should become equal to bulk modulus. So now, we are adding some correction to it. The speed of sound is in fact not equal to just pressure, gamma P by rho, where gamma is called as Cp by Cv, which is called as adiabatic exponent of gas or air. This is a generalized formula we are replacing. So further this we will modify it. Further this will modify it. So then PV equal to nRT. PV mass by molecular mass RT. So this will become P is equal to P by rho equal to RT by m naught. So the expression for speed of wave is given by gamma RT by m naught. This is the expression for speed of sound wave, where gamma is called as the gamma of a mixture, N1 plus N2 gamma in a mixture of gases. Gamma, what are the other formulas? Cv equal to R by gamma minus 1. Cp minus Cv equal to R. So these are the various ways in which in a mixture of gases also we can use. Molecular mass of the mixture is given by N1 M01, N2 M02 by N1 plus N2. This is a gamma of a mixture. Like this in mixture of gases we can put. Speed of sound at any temperature is given by speed of sound at 0 degrees Celsius is equal to gamma R by m naught. This will be 0 plus 273 to the power of 1 by 2. Speed of sound at T degrees Celsius is given by gamma R naught T plus 273 to the power of 1 by 2. Dividing these two, V naught 1 plus T by 273 to the power of 1 by 2. This is the expression for speed of sound. Further this we can write it as T by 546. So what is this? Speed of sound at T degrees Celsius. This is speed of sound at 0 degrees Celsius. This is one formula you have to remember. Then once you know speed, you can also calculate the wavelength. What is the formula for length? Because we know F equal to V by lambda. So there's a wavelength at T degrees Celsius equal to wavelength of sound at 0 degrees Celsius 1 plus T by 546. So we can also calculate the wavelength. This is the wavelength of sound. When a sound wave propagates through a medium, there is a displacement wave. This is a displacement wave, and this is a pressure wave. Where kinetic energy potential maximum when the layers are at mean position. Then at mean position, then this will be maximum compression. So where the potential is maximum, where the compression is maximum, where the potential is maximum, where the rarefaction is maximum. So where the kinetic energy maximum at mean position. So therefore, when the layers are executing SHM, when layers are at mean position, or the layers which are having maximum compression rarefaction will have maximum kinetic energy. So definitely there is a flow of energy. That flow of energy per unit area per unit time we'll call intensity. The intensity is given by, in terms of displacement amplitude, there's a formula. In terms of pressure amplitude, there's a formula. There's the expression for the intensity of sound wave. And there's a diagram you should remember. And what is the theoretical things? When a sound wave propagates through a medium, when those layers which are at mean position, they'll have maximum potential energy, kinetic energy. Those layers which are having maximum compression or rarefaction will have maximum energy. Okay, clear? This is the expression for intensity of sound wave, where the pressure wave is given by, this is BAK, and speed of sound, you can use this formula. And these are some formulas which you can use to solve the problems. There's one very important thing which you have to remember. Next, we will express the loudness of a signal. Rather than responding for the linear scale, we are going to represent for logarithmic scale. So the loudness, we compare we are not comparing ourselves with zero. This will be our reference. Any particular sound signal, I'll compare its strength with respect to this reference point. This will become our reference. This particular sound signal will become a reference. Any other sound signal I'll compare with this, then I say it's okay, louder than this or less louder than this one. So this will be our pain threshold, or also like a faintest signal, what we can call it. Then since I'll represent for logarithmic scale, bell is a very large unit. To make it smaller, I am multiplying with a 10. So 10 log 10, I by I naught. I is the intensity. Then this will become loudness. The loudness is given by symbol beta. The symbol for loudness. Then for 10 to the power of minus 12. So what is the loudness of signal will be 0 dB. For like a signal whose intensity is 1 watt, the loudness will be 120 decibels. And this will be pain threshold. And if any sound signal whose intensity is greater than this, will experience say some sort of pain in your ear. So like this, there's a one unit we brought to express the loudness of a signal. Then we know for a point source, suppose there's a point source of sound which is at a distance x, then what is the intensity there is given by ps by 4 pi x square. There's a point source. Then you can calculate the loudness, beta equal to 10 log 10 I by I naught. The loudness will be 10 log 10. What is the intensity will be ps 4 pi x square, and this will be I naught. So this will become 10 log 10. All this quantity, some put it x square. Like this we can express it here. Then the loudness will be function of the position x. Then we can compare the loudness at various points. The loudness says point 1. Suppose that there is a point source of sound. Then loudness of signal at 1 and 2. Beta 1, beta 2. What is the distance? This will be x1. This will be x2. Then what is the difference in the loudness of that? Beta 2 minus beta 1 will be 10 log 10 alpha by x2 square minus 10 log 10 alpha by x2 square log a by b. So this will become x1 by x2 whole square. Now this will become 20 log x1 by x2. Or if you are taking the difference beta 2 minus beta 1 minus beta 2 will be log of 20 log x2 minus x1. This is one formula. You can compare the difference in loudness depends on this quantity. This is one formula we have to remember. This is about the basic idea of the intensity due to point source, and you can calculate the loudness at any point using this formula, where I naught value will be standard 10 to the power of minus 12 watt per meter square. We'll discuss the interference of sound waves. There is a loudspeaker S1, S2. They are coherent. They are coherent sources of sound. They'll emit waves. This will be rarefaction. The rarefaction there's a rarefaction. And this will be compression. You can see clearly the red and the red yellow when they merge. There are some regions are there, no? We'll get the constructive interference. Here in these regions we have the constructive interference. Constructive interference only. I'll put that one. These are the regions where constructive interference is taking place. And what is the destructive interference? Destructive interference will be the region where the compression rarefaction will undergo superposition. Hope you are able to get this one. So because of this superposition of waves, we'll get the resultant intensity. So what is the basic formula? We know the intensity of each source is I1, I2. Basically, what is I1? I1 equal to I2 equal to I0. Because we'll be discussing superposition of waves near to the source. Let y is equal to y1 plus y2. A sine omega t minus kx. Then A2 sine omega t minus kx plus phi. Different waves. So this wave will cover a distance r1. This will cover r2. Due to that path difference r1 r2 will get the phase difference. So then the resultant equation is given by AR sine omega t minus kx plus phi. So the resultant intensity IR is equal to I1 plus I2 2 root I1 I2 cos phi. The cos phi, the phase difference depends upon the path difference. A wave 1 will cover path x1, wave 2 will cover path x2. The difference of this path or R2. Due to difference in this path, we'll get the phase difference, and that phase difference will determine what is the resultant intensity. Since I1 equal to I2 equal to I0, no? So this will become 2I0 cos phi. The resultant intensity is given by 2I0 1 plus cos phi. 4I0 cos square 5 by 2. This will be resultant intensity at any point. What do you mean by destructive? Where the energy will cancel out. Plus A minus A. Resultant will be 0. What do you mean by constructive? Plus A will be 2A will become, the resultant amplitude will be 2A. Intensity will become 4I0. At maximum intensity. So here at for destructive interference, the resultant intensity will be 4 I naught. The resultant intensity here will be 0, because for constructive interference, what is the condition? For constructive interference, cos phi should be equal to plus 1, then the resultant intensity will become 4 I naught. And what will be the path difference? Path difference should be equal to n lambda. Then for destructive interference, now for destructive sound waves, cos phi should be equal to minus 1. Then the resultant intensity will be 0. Path difference should be equal to 2n plus 1 lambda by 4. There's a condition for constructive interference. The path difference of the waves arriving at a point is n lambda, like a 0 lambda, 2 lambda, 3 lambda. Constructive, if it is something like 2n minus 1, will start it. Lambda by 2, 3 lambda by 2, 5 lambda by 2, then it will be destructive interference. The path difference. We will determine the path difference at what distance the sound sources are located from a particular point. We have two sources of sound. This will emit rays which will cover a path of how much? 13 meter. This will emit a rays which will cover a path of how much? Say like a root 13, this one. So this will cover a path R1, this will be R2. We'll calculate the path difference. First, what is R1? 13 meter. What about R2? R2 will be 10 square, 13 square. 100 plus 169. 169. This will be 269. Okay, we'll get these are the path. Then path difference equal to R2 minus R1. 16 minus 4 minus 13. 3.4 meter. Then what is the phase angle? 2 pi by lambda into delta x. 2 pi lambda is how much? 3 meters. Delta x 3.4. The phase will be 3.4 divided by 3 will be 1.13. 1.13 into 2, 2.26. Then we'll calculate the resultant intensity at the location of person. I1 plus I2, 2 root I1 I2 cos 2.26 pi. What is I1 further? I1 is equal to power P naught by 4 pi R1 square. I2 equal to P naught power 4 pi R2 square. P naught, let it be 10 watt. Power of each source. Like this, we can calculate the resultant intensity at the person. This is a basic method of the interference, working out interference problems. Just a simple idea, need not to go in detail, just a general idea. The resultant intensity at this point depends upon the path difference between the waves. The path difference between the waves will determine the phase difference. The phase difference will determine the resultant intensity. Next, we'll discuss the organ pipes. A reflection of sound at the closed end. There's a tuning fork which will generate sound signals of frequency f. The wave generated will go like this. Then this will arrive here. This will call by I. Okay, this will be incident wave. Then as reflected by closed end, so it will undergo phase change of pi radian. This is basically, we know if a wave reflected by a closed end, it will get reflected by a closed end or rigid end. Both are same, no? Will get inverted by this will get inverted. Then we know the pressure wave. If the compression here will be reflected as rarefaction, and the rarefaction will be reflected as compression. So the displacement wave will not undergo phase change. The pressure wave will undergo phase change of pi radian. There is one basic concept which you have to remember. The reason for that, if y is equal to yi is equal to, this will be compression. So this will be a sine kx minus omega t. Delta b equal to minus dy by dx minus b a k cos kx minus omega t. What about the reflected wave? This is the incident wave. Then the reflected wave. For the reflected wave, what is the equation? We'll write it. Yr is equal to a sine k minus x minus omega t plus phi. A sine minus of a sine minus kx minus omega t. So this will become a sine kx plus, or this is a displacement wave, will be inverted. What about the pressure, reflected pressure wave given by minus dy by dx? This will become minus of minus plus in compression. So this will be no. Okay, this will be derivative of this will become ak cos kx minus omega t. So again I'm getting the same equation. So look at this, minus bak minus bk. If this is the compression, this will be compression. So therefore, for a sound wave, when it is compression is incident, it will be reflected as compression. If a rarefaction is incident, will be reflected as rarefaction. So which particular phase change will occur? Displacement wave will undergo phase change at closed end, reflection of sound at closed end. Displacement wave will undergo phase change. Pressure wave will not undergo phase change. So this is one basic idea what we can reflect here. Undergoes phase change. I'll write it here. So the displacement wave will undergo phase change of pi radian. Pressure wave will not undergo phase change of pi radian. No phase change. These are the basic ideas of reflection of sound at closed end. Similarly, we'll go for the open end. Now this will be, it will generate a sound signal. Here there is an open end. Here we'll get the displacement wave will get reflected, and we know the reflected wave will not undergo any phase change. Whereas the compression will be reflected as rarefaction. The pressure wave will undergo phase change. So how you can show that one? So we'll choose the equation y is equal to a sine kx minus omega t, or omega t minus, anything you can choose. Omega t minus kx. It get reflected. Omega t minus kx will become a sine omega t plus kx. What about the pressure wave? Pressure wave will be minus dy by dx minus bak cos omega t plus kx will become positive. Derivative of sine minus k will become positive. Dy by dx equal to minus bak cos omega t plus kx. Okay, what do we get here? The compression will be reflected as rarefaction. Rarefaction is compression. So will undergo phase change. Displacement wave, no phase change. Pressure wave will undergo phase change. Phase change of pi radian. There's a one property here. The compression will be reflected as rarefaction. Rarefaction as compression. Nature of sound signal will change. Whereas the displacement wave will not undergo any phase change. And these are ideas. Next we have the closed end organ pipe. I'll send the sound wave here. The incident wave will get reflected. The incident and reflect will undergo superposition and we'll get here a standing wave. So how do that particular standing, this will be closed end organ pipe. So what is the conclusion? So if you go back to this, what is the conclusion we'll make it? The closed end must be a displacement node, pressure antinode. Closed end, displacement node, and it should be a pressure antinode. What about the open end? The open end must be displacement antinode, pressure node. So here pressure node, like this. We're making conclusion. So based on the same idea, for closed end organ pipe, there's an open end, so therefore this should be like a displacement antinode, or pressure node, pressure antinode, pressure node. I'll show only first displacement node. So again this will be one end of loop. Next, the length of the loop should be called lambda 2 by 3 by 4. The resonant frequency will be first overtone or second harmonic. This is called a fundamental tone, F1 equal to V by 4L. First overtone will be 3V by 4L. One end of half loop, one end of loop, two end of loop, three end of loop. Length of the tube is constant, and these are the conditions. So as usual, this will be displacement node, antinode. This will be displacement antinode, displacement node, displacement antinode. Or in terms of pressure nodes, we can write it. The generalized equation 2n minus 1 V by 4L. What is V? V is the speed of sound signal. Like this, in the closed end organ pipe, a resonance frequency is set up. How do this condition? You can see there's a closed end organ pipe. There's a closed end, there's an open end. The waves will come from here, will get reflected. Here this will be displacement node. This particular thing will never vibrate. You can see this one. There's a node. Then here air column length. So we are making one loop. So here I'll change the wavelength. This will be node. We can determine like a node antinode. This will be displacement node. Okay, further if I decrease, this will be displacement node. This will be displacement antinode. Like this I can adjust this. So I'll keep the length constant. I'll change the wavelength. No, this will be select here one loop, 1.5 loop. Next, by changing the wavelength, what we can see the vibrations. Here the particles will vibrate horizontally. What about this green color and red color? They are the, just I'm showing the amplitude of vibration along y-axis. Actually, how the particles will vibrate here, this will be node, this will be displacement node, this will be antinode, this will be antinode. Like this, the waves will be, the standing waves will be set up. Here they'll be vibrating here. The particles will be oscillating. You can see clearly here. There's a displacement node. This layer will not vibrate. Next again, this layer will not vibrate. All other layers will be vibrating. The layer which will not vibrate will become displacement node. Resonant frequencies of the air column. These are for closed end organ pipe. We are bringing it here. Similarly, we'll go for the open end organ pipe. For open end organ pipe, both ends are open, so this will be displacement antinode. This will be node, antinode, antinode, displacement node, antinode, antinode, node, node. This will be node. This will be displacement antinode. Then lambda 1 equal to L, 2 off loops, 1 full loop, 2 off loops, 2 full loops, 2 off loops. Then these are the resonant frequencies. Then we'll get all harmonics are NB by 2L, where V is the speed of the sound. These are the resonant frequencies for open end organ pipe. I'm showing the displacement standing wave. Okay, next we have the resonance air column experiment. It's a very simple one. There's a tuning fork of frequency F which is vibrating. There's a air column. The yellow color one is air column and there's a glass tube. The length inside that will determine the resonance things. So I'll keep the frequency of the tuning fork, let it be F. So first it will resonate. So the resonating length will be L1. Next, the same tuning fork is kept here. The same tuning fork again of frequency F is brought here. Then here frequency F, F and this F. Now resonating length will be L2. Now resonating length will be L3. Now this will become closed end and this will be open end. Then the length will be L1 equal to lambda by, so L1 equal to lambda by 4. L2 is equal to 3 lambda by 4. L3 equal to 5 lambda by 4. Then I'll take the difference L2 minus L1. 3 lambda by 4 minus lambda by 4 equal to lambda by 2. L2 minus L1 equal to lambda equal to V by 2F. So the speed of sound, by measuring L2 and L1, we can predict the speed of the sound. This is the expression for speed of sound. What is F? F is the frequency of tuning fork. And L2, L1 we are going to measure. At here we'll get maximum sound. At resonating length we'll get the maximum sound. We'll take the next condition. Now we are going to discuss the end corrections. This will be the tuning fork will be vibrating. It will make the air column to resonate. The oscillations which are present at the open end will get extended beyond the length of the tube. So then the actual wavelength will should be measured from here. So E plus L1 should be equal to lambda by 4. Similarly, the oscillations will get extended beyond the length of the tube. Then E plus L2. L2 is the physical length what we can measure. This E we can't measure. So this should be equal to 3 lambda by 4. So that's lambda by 4. Now we can replace it as E plus L2 equal to 3 by 4 E plus L1. So this will be E minus 3E by 4 equal to 3L1 by 4 minus L2. This will be E is equal to 3L1 minus 4L2. Some correction, so lambda by 4. This will be only this much. This will be, the corrections will be 2E equal to 3L1 minus L2 equal to 3L1 minus L2 by 2. Now there is one formula for n correction, where this n correction physically they'll be related to the diameter of the tube or the radius of the tube by the formula equal to 0.6 r. Like this we can estimate the n correction in terms of the radius of the tube, or you can calculate by experiment using this particular formula. So therefore like this we can know for closed end organ pipe, for open end organ pipe, for closed end organ pipe there will be n correction at the one end, then the resonant frequency is given by 2n minus 1 V by 4 L plus E. The resonant frequency at open end organ pipe is given by NV by 2 L plus 2E. Now why here 2E? There will be n corrections at both the ends. There is one formula where this n corrections will be related to radius of the tube. So where E equal to 0.6 r. There's a direct formula base which you are supposed to remember. Next topic will be the beats. There are two sources of sound of different frequencies. They will generate a sound signals. The superposition will be wave of this kind of, where the amplitude will be varying with the time. As amplitude varies, the intensity will vary. As the intensity varies, the loudness will vary. So this person is going to hear a sound signal where the loudness will be varying with the time. That's one basic condition. So there's a sound signal of frequency F1 generated by loudspeaker 1. There's a sound signal of frequency F2 generated by loudspeaker 2. They'll undergo superposition. Then we'll simplify this. I'll end up equation of like this. Then here this equation will be of this kind of y equal to a of t sine 2 pi ft. What is f? F is the frequency of the resultant wave. A of t, the amplitude of this will be varying. How did it will vary? It will vary in one particular order. That's given by this equation. That this whole quantity will become amplitude. And it'll be. So when I plot this amplitude as a function of time, I'll get here. This will become one cycle. This part is getting repeated. So in amplitude versus time graph, you want to calculate the beat period. So the distance from the positive to negative peak is what? What is the beat period? Or you do one thing, square this, will get intensity, and plot that intensity versus time graph. Then this will become one cycle. Time taken for the intensity variation to complete one cycle is called beat period. The reciprocal of beat period is what we'll call it as beat frequency. So what is the beat period? The beat period is reciprocal of the beat frequency, beat period. Then what is the beat frequency? Beat frequency is just equal to F1 minus F2 from the graph. To substitute some values, everything, this will become. So the difference in signal frequencies. The difference in frequency of the signals of two sources will lead to bit frequency. So FB equal to F1 minus F2. This will become bit frequency. How to calculate the bit frequency afterwards? Difference in frequency of two sources, that will become bit frequency. The reciprocal of bit frequency will become beat period. What is the beat period? Time taken for intensity variation to complete one cycle is called as a beat period. So now two tuning forks are there. What is the earlier beat frequency? The beat frequency is equal to F1 minus F2, which is equal to 20 minus 16 4 hours. Now the first tuning fork fork will be as it is. Second tuning fork, I'll apply some wax. When I apply some wax, definitely the beat frequency will decrease. So let it become say like a 15 Hz. Now what will be the beat frequency? No, the new beat frequency will be f1 minus f2 dash 20 minus 15, 5 Hz. So by applying the wax, what will happen? If the beat frequency increases, then to which tuning fork we applied wax? We applied wax to the low frequency tuning fork. Now similarly, we can bring the, I have two like a tuning forks of frequency 20, 16 Hz. Earlier frequency is 4 Hz. Now I apply wax to the higher frequency one. Then what is the new frequency will become 18 Hz. The new frequency will be now 18 minus 16 will be how much? 2 Hz. If the beat frequency decreases means we applied wax to the tuning forks whose frequency is higher one. Like this, by applying wax, the frequency of tuning fork decreases. By filing the tuning fork, the frequency will increase. These are some problems are there. Now there can be tuning fork, two tuning fork and the vibrating string, tuning fork and organ pipe. Like a vibrating string and organ pipe. So many conditions will come. Try to analyze once. Last topic, we have the Doppler effect. So when do we can see Doppler effect? When there is a relative motion between the source and the observer, then the frequency, there will be the actual frequency is f0. Then the measured frequency will be f. If the observer is at rest, then he is going to receive sound signals at frequency f0. When the observer is moving, then he is going to receive the sound signals at a frequency other than the actual frequency. This will become apparent frequency. This will become actual frequency. Okay, fine. So the apparent frequency is given by this one. This f0 is called as like an actual frequency. What is f? F is called as apparent or measured one. So when the observer is approaching the source, then the formula will be v plus vf0 by v plus v0. v0 is the velocity of observer and stationary source. Similarly, the apparent frequency when observer is at rest and the source is approaching it, then the apparent frequency is given by f equal to f0, v minus vs by vs is velocity of the source or velocity of the truck. Then the apparent wavelength also is going to change. Next here, so this is observer 1. So actual frequency of source is how much? f0. Is going to receive at frequency f1, f2. So what is f1? f1 should be equal to fv by v minus source is approaching it, v minus vs. Similarly, the waves emitted this. The source is moving away. The source is moving away. So the apparent frequency is given by fv by v plus vs. Like this we can define the wavelength. So then the wavelength emitted lambda 2, lambda 1. What is lambda 1? Lambda 1 will be v by f1. What about lambda 2? V by f2. As f2 is less, so wavelength will increase. So the wavelength received by the both observers will be different here. The same conditions will arrive here. When truck is at rest, the wavelength will be same. When the truck is moving, this wavelength and this wavelength will be different. That I am showing it here. When both source and observer are moving. When both source and observer are approaching each, when source and observer are approaching, f dash equal to v, source is approaching, so v minus vs f0, observer approaching v plus v0. Then what about the wavelength received? Wavelength received will be lambda dash equal to speed of sound by f dash. So with what speed the waves will strike in v plus v naught. Substitute this f dash lambda equal to v by f. So f dash equal to how much will be v minus the observer is approaching. This will be source. No, we can write here. So what is v plus observer approaching? Source approaching will be v minus vs. Then this is the wavelength will be lambda dash is given by v plus v naught by f dash will be v minus vs by f naught. Similarly, observer moves away v minus v naught f naught. Source moves away v plus vs. The wavelength, apparent wavelength is given by v relative by f dash. V relative will be v minus v naught by f dash. V minus v naught by f dash will become v plus v by f naught. In this case, apparent frequency, this will be v, observer moves away, source approaches, v minus vs. Lambda dash equal to v minus v naught by f dash. This will be the wavelength. Similarly, f dash equal to source moving away, source will approach the observer, v plus v naught into f naught by v plus vs. So lambda dash is equal to v plus v naught by f dash. Okay, like this we'll get the wavelength. Apparent wavelength, this is actual frequency, this is apparent frequency. Wave is propagated, the wind is blowing. What is VW? Wind speed. So the wave will propagate in the direction of wind. The effective speed will be V plus VW. So then in this case, the apparent frequency is given by V plus VW minus Vs into F naught V plus dW by V naught. If the wind blows in the direction of wave, effective speed of sound will be V plus VW. Then the apparent frequency as second case will be V minus VW. If the wind blows opposite to the direction of the wave propagation, V minus VW minus Vs F naught V minus Vd plus V naught. If the wind blows in the direction of wave propagation, then effective speed of sound is V plus VW. If the wind blows opposite to direction of wave propagation, then the speed of the sound should be V minus VW. If the source and observer, if they are moving in some different direction, then the Doppler effect, here it will generate a signal F. It will be received at F dash, where the apparent frequency is given by V minus Vs cos alpha. Component of velocity measured along line joining source and detector should be substituted in Doppler effect. Then this will become V plus V naught cos beta. Component of velocity of observer along line joining the source and detector. That will determine the apparent frequency. Okay kids, we have the discussion on the waves and sound one shot. Waves and sound one shot. So I covered exclusively almost all the ideas of the waves and sound. We started with how the wave propagates, types of the wave, then wave equation, y equal to a sine omega t minus kx, y omega t plus kx, or the amplitude, frequency, time period, altogether wavelength, then time taken by the wave to propagate to a string, then phase of a wave, then energy, power, intensity of wave, then how to write the wave equation, all that it was on a stringer. Then it was a transverse mechanical wave. Then if a wave reflected by rigid and free end, then the refraction of a wave when wave moves from one medium to other medium, all the formulas exclude. Then we discuss the superposition of waves, transverse waves on a string. Then we discuss the standing waves on a string. Then we went for sound wave propagation. When sound wave propagates to a medium, pressure, density, and the layers will undergo execute SHM, we brought mathematical equations. Then we brought the speed of sound, expression for speed of sound. Then we express the amount of sound signal loudness. Then interference of sound waves, like if we had constructive, destructive using two loudspeakers. Then organ pipes, closed end or open end organ pipes, and correction, determining the speed of sound using the resonance air column method, all the formulas. Next, the beats, a very small topic. The difference in signal frequency of two sources is the beats. What is the beat period? The time taken by the intensity variation to complete one cycle is called as the beat period. Reciprocal of that beat frequency. Then Doppler effect. Whenever the source and observer, when there is a relative motion between them, the measured frequency will be slightly different than actual frequency. That's called like an apparent frequency. All cases we have discussed. So there's a general idea, very lengthy chapter, lot of content is there and lot of formulas you have to remember. There's a one strategy, try to follow it. So first concept clarity, then the formulas, concept clarity, formulas, then go for PYQ. You can do better in the exam. Now without concept clarity, now you try to remember formula, no use. So you must know all the concept, how the wave reflected by closed end, rigid end, what is meant by open organ pipe, how the concepts clarity, then formulas, then solve PYQ. There's a one chronological order, you have to follow it. Okay, I'll end up this. Okay, thank you for great support. I'll end up the session.